All right, Module 2, Day 1. Begin Module 2 on page 37. Stop after doing on your own 2.1 on page 39. Are you sick of one-dimensional motion yet? I hope not, because we have another entire module of it ahead. You see, while module number 1 laid a good foundation for understanding the basics of one-dimensional motion, it did not go into enough detail or depth. One-dimensional motion is so important in physics that we must learn a great deal about it. As a result, this module is also dedicated to that important subject. While module number 1 set up the basics of one-dimensional motion, this module will explore the many applications of that subject. In this module, we will develop 3 very important equations that will allow us to describe many situations which occur in one-dimensional motion. And in addition, we will concentrate on a very prevalent form of one-dimensional motion called free fall. Whenever any object is falling towards the earth without anything inhibiting its fall, we say that the object is in free fall. If you think about it, things fall all of the time. So free fall is obviously a very important subject. That's why we will concentrate on it in this module. Relating velocity, acceleration, and time. In order to be able to solve any type of one-dimensional motion equation, we will have to learn 3 basic equations. The first of these 3 is based on equation 1.3, and that is acceleration equals the change in velocity over the change in time. As we learned in the previous model, A is acceleration, delta V is the change in velocity, and delta T is the change in time. Now, remember, delta V can be calculated by subtracting the initial velocity from the final velocity, and delta T can be calculated in a similar manner. So let's go ahead and write that down. So delta V can also be calculated with V final minus V initial, and the change in time can be calculated the same way. T final minus T initial. All right, now we're going to make a simplifying assumption. Let's assume that whenever a situation begins, that T initial will always equal 0. This way, the equation is a little bit simpler. So again, we're going to assume right here that T initial will always be 0. So our formula can then become the acceleration is V final minus V initial over T final. We can just get rid of the T initial because we're assuming it's 0. So we have a little bit of a simpler equation right here. All right, next, let's rearrange this equation using algebra. So let's go ahead and solve for V final. So to solve for V final, we have to multiply both sides by T final. So we get acceleration times T final equals V final minus V initial. And now the last thing we have to do is get rid of V initial over here, so we have to add it to both sides. So we have acceleration times T final plus V initial equals V final. All right, so we just rearranged everything to solve for V final. Nothing hard there. All right, as a final adjustment to this equation, I am going to rename a couple of these variables. Since most problems want to know things about the final state of a situation, I'm going to rename V final to just V. All right, so V final going forward will just be called V, and T final going forward will just be called T. They mean the exact same thing. I am just making them easier to write. Finally, I will also make V initial easier to write by calling it V naught. This will now be called V, and that little zero down here is naught. With these new symbols, the equation becomes V equals V naught plus AT. This is a very important equation that we're going to be using all the time. So that equation is the first of our three new one-dimensional motion equations, and it is very important, and that's why I have to put it in its own box. Well, what does that mean? It means that I can figure out the final velocity, which is this, of an object by taking its initial velocity and adding the acceleration times the time. You will use this equation over and over and over in this module and in the ones to come. So you should commit it to memory now. So once again, go ahead and just plan on memorizing this equation right there. As a brief aside, everything that you've read from the beginning of this section to the end of the previous paragraph is called a derivation. In the science of physics, we do this quite a bit. In general, a derivation starts with something that you already know and uses math and reasoning to come up with something brand new. Although I presented the derivation of this equation right here as a means of helping you understand where the equation comes from, there is no need for you to be able to reproduce it on your own. Thus, although you should understand the reasoning I just went through, the only thing you really need to remember is equation 2.6, which is this, and how to use it. This will be the general philosophy for this course when it comes to derivations. If I present a derivation, you should try to understand it, but you will not be expected to reproduce it or any of the equations in it. The only thing you will be expected to really remember is the final result and how to use it. So don't worry if a few of my derivations go over your head. Just be sure you can use the final equation that is produced. Now that we have this out of the way, let's see how we can use equation 2.6. Let's go ahead and look at on your own 2.1 on page 39. A car traveling at 35 meters per second, about 78 miles per hour, passes a police car which is moving at 23 meters per second, about 51 miles per hour. The policeman does not have a radar gun, so he immediately starts to speed up in order to match the speeder's velocity. That way, he'll be able to measure how fast the speeder is moving. If the police car can accelerate at a rate of 2.5 meters per second squared, how long will it take for the policeman to match the speeder's velocity? All right, we should always start with writing down what's been given in the problem. So on your own, 2.1 on page 39, let's list out what is given. Okay. It tells us the final velocity. So again, V final, which we just renamed as V, equals 35 meters per second. Acceleration is also given at 2.5 meters per second squared. And V initial, which we just renamed as V naught, is 23 meters per second. Again, that's what's given to us. Now, what are we looking for? The unknown in the problem. We are looking for how long or how much time it will take for the policeman to match the speeder's velocity. So we're looking to solve for t. And since the policeman is speeding up in this direction, we know the acceleration to catch this car. And since we know the policeman is speeding up, we know the acceleration and the velocity have the same sign. So we're gonna call that direction the positive direction. All right, so now we have to figure out what equation will help us solve this. We can go to the one that we just learned. V equals V naught plus AT. So once again, we know V, we know V naught, and we know A. So we have to solve the equation for T. So we can rearrange it algebraically and solve for T. So to do that, we need to get rid of the V naught on this side. So we can say V minus V naught equals acceleration times time. And now again, we have to still solve for time. So we have to divide both sides by acceleration. So T equals V minus V naught over A. So that's the equation that we're gonna use. So now we just have to put all of our values in. So V final, or V, was 35 meters per second. So 35 meters per second minus V initial, or V naught, is 23 meters per second over the acceleration, which is 2.5 meters per second squared. All right, so when we do the math, we have 12 meters per second over 2.5 meters per second squared. All right, so the meters cancel out and one of the seconds cancel out, so we're only left with seconds. And considering we were asked to figure out time, it makes sense that we're left with seconds. So T equals 4.8 seconds. The policeman needs 4.8 seconds to match the velocity of the speeder.